Okay, so this is we were moving on to homework number 7, and number 7 is the kind of finale, the last one of a series of 3 homeworks. And these 3 homeworks you are working on, you're currently working on sinusoidal modeling. And so let me just show you the start right away. Okay, so today we will be okay. So yeah, so let's begin. Today's homework, this week's homework, by the way, this is going to be a 2-week homework. So it's going to be slightly, you'll have double the time to work on this homework. And this homework is going to be about sine plus noise decomposition, okay, separating the same signal into 2 components, decomposition. And then by doing that, essentially you will be able to create a format, let me say that. Because in audio file, we know that if we just sample the signal, you get the WAV format. And if you compress using any widely available formats, such as MP3 or Apple AAC, which is also has the file extension as MP4. So those are different formats. So essentially, after today's homework, you derive a format where you can kind of describe or represent or encode sine and noise parts separately. And then thus you essentially we're going to achieve data compression. So that's quite a important topic and question. Oh. So let me just still allow more people to join. We have most of people now, still a few coming in. So thanks for joining on time. And so let me just slowly begin today's lecture. Okay. Okay, so a bit of a recap where we are at right now. So you've just turned in the homework last night. And that homework was about trajectory formation, right? So we have peaks that are detected for each frame, and you manage to continue the trace to connect the peaks across different frames, from one frame to the next. And sometimes a new peak can show up, where the old peak would stop to continue. Will be not allowed to continue. So we are handling you, some of you, I believe, actually, I believe the requirement of homework 6 is to handle the birth and death of trajectories, okay? So we mentioned in last week's lecture that if your tracking is backward, then you will basically find the shortest link and then resolve the splits whenever necessary, okay? And also, the idea of trajectory is that really from one peak to the next, really we don't want to allow too far of a jump, okay? So how large is too large? And you can come up with different ideas, and that is great. And so also, as I mentioned, birth and death should be already handled. And so, and also there's an issue that whether or not your synthesis algorithm can run in real time. And so these are different issues. And so how about this week? So this week, so this is kind of a list of objectives of this homework. So first of all, we are going to do decomposition, right? The title, the topic of this week is, let me see if I can move this around. This week's topic is about signal plus noise, not a signal, sinusoid, sine plus noise decomposition, right? So decomposition means to separate one signal into 2 components, okay? So in a way, in the previous homework, you have extracted the sinusoid, where they are represented, they show up in the spectrum as peaks, right? So you, for each frame, you have estimated the amplitude envelope, the frequency envelope, as well as in principle, you can also estimate the phase of each peak because the spectrum is a complex number, right? So each peak should also be associated with a phase, right? So now these are, so roughly what a trajectory is really is a kind of it consists of three parts: the amplitude envelope, the frequency envelope, as well as the instantaneous phase for every frame. Okay, so once you figure those out, and in this homework, you will be asked to remove the sinusoid from the original signal so as to achieve a separation. So let me put it this way. So you are going to separate the signal into the sine part and the residual. What remains in the signal then becomes more, I'll have some sound examples today. What remains in the spectrum after removing all the peaks will sound like noise or filtered noise. Okay, let me still allow one more person to join. Welcome, Wanzhen. Okay. Okay, so that's the first objective of this homework. You will remove the sinusoid from the original signal. And then after that, the residual, as I mentioned, should sound like filtered noise because all the peaks representing sinusoid, right? Sinusoid have frequencies. They have, the sinusoids are oscillation and they can sound more like a combination of tones, as we all know by now. And so after removing all the sinusoid, the remaining, what remain in the spectrum or in the signal should sound like filtered noise. And if you successfully achieve the goal that the residual now sounds like filtered noise, then because they sound like noise, you will model it as what? As white noise or Gaussian white noise that is filtered by an all-pole system. All-pole system meaning you will be applying linear prediction coding, the idea that you have encountered in homework number 3. Okay, so it's 2 steps. First step is to remove the sinusoids, and second step is to encode, basically, to represent the residual as filtered noise, filtered Gaussian white noise. Okay, so we deal with the sine part in the previous homework. We represent the sinusoid as trajectories, as well as now the residual part can be encoded by filtered white noise. Okay, then essentially we have 2 subsystems, one handling the sinusoid, the other handling the residual. So you will already decompose the signal into what is called sine plus noise. And then by representing them differently, the sines will be represented by the amplitude and frequencies, how they change location, and the amplitude can vary in time. And that you have done that for the previous 2 homeworks. And also in this homework, you will represent the noise by what? By the magnitude and in conjunction with the linear predictive coefficients. Okay, thus you in principle achieve data compression. And okay, so that's the idea. Okay, and any questions so far? And this is going to be a group homework for 2 weeks. Okay, so I'll tell you in the end of this lecture what I expect you to work on, each group to work on for number 1, week number 2. So next, let's finally come to this block diagram. Right. So this slide shows the entire flow. So I've spent a lot of time working on this slide. Right. So the information flow of the update, so actually I will, these blocks you'll find them in the starting code. Okay. In the starter code which I already uploaded to eLearn. And so the idea is that we have one input, okay? And then we will create 2 outputs. And that's the meaning of decomposition. 1 input, 2 output. The input is going to be decomposed into the sine part, which is essentially your result for homework number 6, okay? And also the noise part. After removing the sine from the spectrum. So how do we do that? Let me explain the blocks before before showing you the example. Okay, so let's say we have the input and we know that in the analysis part for sinusoidal modeling, we are using FFT with 0 padding, and then after that, because of 0 padding, we have finer resolution in the frequency, so that we can estimate the peak by fitting a parabola. So that's homework number 5. But then what's different this time really starts here, right here, okay? So in the past 2 homeworks, you extract the amplitude and frequency envelopes, and you are allowed to track up to so many tracks simultaneously, be it 20 or 50 or 80, okay, number of tracks, okay? And but in this time, we keep this information, but then we also in this article, I've done this for you. Also, in this time, we need to keep track of the phases of all the peaks, okay? The complex exponential, the real part, marginal part, the phase, okay? We need to keep track of both the real part and the imaginary part. What for? So we do that so that we want to do the decomposition right here. Okay? That's where the decomposition is happening. So, but before we explain that, we'll come back to this, okay? But otherwise, you'll notice that the amplitude and frequencies are used for trajectory formation, which is the concept number 6. And then after forming the trajectory, you can use additive synthesis and then synthesize the sine part. So let me play you the sound right now.
Draw every outer line first, then fill in the interior.
So, for example, by now you should have come up with even if things done correctly, more or less, you should be able to synthesize the sinusoidal modeling results, and the property, the quality should be close to this one.
Draw every outer line first, then fill in the interior.
That's your previous homework. That's your previous homework. But what's new in this homework really starts from here. So this bottom route is the requirement for this homework. Okay, so it consists of this part. So first of all, the first step is to also estimate the phase, and then use the amplitude, frequency, phase. And the third, then jointly specify exactly how the sinusoid should occur in the time domain, right? Amplitude, frequency, and phase. And so using these, I'll show you the equation. But conceptually, you will perform a single frame based synthesis, and let's call that the result sum of sinusoid, denoted as sine sum. Okay, that's the variable name in my code. And then from there, you subtract the sine sum from the original signal. Okay, let me say that again. You subtract the result of sinusoid, single frame synthesis from the original signal, and the remaining part should be kind of free from any harmonics. Let me say that again. After removing the sum of sinusoids from the signal, the sinusoids that you keep track of will already be removed. So that if you remove enough, sufficiently many sinusoids, all the prominent ones, if you remove all of them, the remaining should sound like noise. So that's the idea of decomposition right here. Okay. Any questions so far? Any question right here? So let me play you the sound. So this is the result of removing all the sinusoids. The should sound like, hopefully it should sound like something like this.
Draw every outer line first, then fill in the interior.
This sound is almost without the kind of tone quality. It is kind of, how do I say, in Chinese, it's 沙哑, okay? It seems like there's not a clearly definite pitch in this signal. Let me play that again.
Draw every outer line first,
so that's the result of after removing all the sinusoid from the signal, okay? And then further, so actually by now you have achieved sine plus noise decomposition. So you might argue if you add the two signals back, would it sound like the original? And the answer, I will show you an example. But before we show that example on the next slide, I want to continue to talk about now after we decompose the signal into the sine part and the noise part, and to achieve data compression, you also need to or store or represent the noise concisely or efficiently, okay? So as to achieve data compression. So here I'm suggesting you to use the knowledge you already have in homework number 3, right? So remember that in homework number 3 we talked about linear prediction. So for a noise like this, it's wideband, so it's kind of nice. It's actually pretty nice that indeed we can model this signal using the technique of linear prediction. Okay, so what's happening is that in this after you synthesize, you decompose the signal into this noise part.
Draw every outer line first,
then
fill
you
in the
will
interior.
start processing the noise alone. Okay, you process the noise alone by first applying rectangular window to chop a block to obtain to perform blockwise processing. And then for each block, you run LP, linear prediction coefficients. Okay, you remember that linear prediction is, the idea is what? Is to represent every current signal as a linear combination of past signals. And you need to determine what is the order of your linear prediction, okay, call it P. And then in that, the problem can be formulated into a least square problem. So where you find the best coefficients to give the best prediction with the smallest error, right? So that's the idea. And please remember that in homework number 3, we also talked about the idea that actually the residual can be thought of as your excitation source, either the source from the throat, from the glottis, 这从声门发出来那个 source, excitation source. And in this case, because our signal, we begin with a signal that is kind of void total quality. It really sounds like filter noise. So after, remember that LP, the idea of LP is to whiten the signal. Okay, so after the whitening is really done well, you can expect that the residual should really sound like white noise, which means that white noise is characterized by only one parameter. White noise, an instant of white noise all sound the same. All instances of the same white noise, the same magnitude or same variance. Variance being sigma squared, as we'll see later in equations. So really, to represent white noise is very simple. You don't need to describe the entire signal, but instead you describe only the variance. The noise is like varying, right? But you only need to describe it is IID. Then you only need to describe the magnitude, the variance of the noise. So which is pretty nice because then you will be already describing the kind of encoding, representing the signal with only P plus 1 parameters, P of them being the LP coefficient and 1 being the variance, the standard deviation of the white noise. Okay, so that's the idea. So once you reach that very concise, compact representation, then you can, in the player side, you can construct the signal, reconstruct the signal into something that sounds similar. So now press this button here to let you hear whether or not the resynthesized noise sounds similar to the residual noise that we begin with. Okay, so here comes the resynthesized result.
Draw every outer line first,
here
then
was
fill in the
residual.
interior. Draw every outer line first, then fill in the interior. Draw every outer line first, then fill in the interior. Draw every outer line first, then fill in the interior.
I feel like I want to pause a bit. Any comments so far? Any comment? Any comment? I hope this is an interesting exercise. Yeah, this is like playing magic. One input, two output, right? I personally found it to be quite interesting thing to work on. Okay, so again, please feel free to interrupt me anytime, okay? Because otherwise I'll just keep talking. All right, so the next slide, I'm going to show you, before we show the details of implementation, I want to show you kind of a perspective, okay? So let's sit back and think of the kind of the entire flow I just presented to you. What does it really mean? Well, in practice? So it really means that we are achieving data compression. And just to be kind of play cool, let's call our format 5, right? MP3 is MP3, MP4 is the Apple format, Apple file extension. Let's call our format MP5. You can really have the right to name it, right? MP5, which is 6, MP whatever, 23. Right. So the idea that we have the input, which is originally in 44.1 kilohertz, 16-bit format, and you have a file rather a file size. And then what we essentially are doing, by the way, in the previous slide, the yellow thing shows that the thing that you actually need to store. That the only thing that you need to store. Okay. So among those, so the same. Yeah. Let me just briefly go back one slide. So these are yellow tags, yellow boxes are the data that you need to store in order to the only data you need to store for replaying the signal somewhere sometime. Okay, the kind of data storage. And so coming back to this, so let's think about this. Look at this. So the only data you need to store are two parts. One is for noise part, and the other one for the sine part. For the sine part, you store the amplitude of peaks and the frequency of peaks. Okay, is that right? So you have done your homework sick. You know what I mean. By now, it should be pretty clear that only thing you store for the sine part is the amplitude and frequencies of the peaks, right? And so the kind of amount of data will be equal to the number of tracks times the number of frames, naturally, for each of them. And for the noise part, I just try to convince you that you only need to store up to P coefficient, LP coefficient per frame, plus one coefficient for the noise narrowness. Okay, so P plus 1 times number of frames for your signal. The sine part storage, the noise part storage, plus maybe a few more bytes to describe the kind of hyperparameters, the frame rate, the sampling rate originally, and also the order of LP and what is the total number of tracks, total number of frames. So you might need to store it in the header as a header. So in your file format, you can totally imagine you have a header and then followed by data structure. Okay, so this is really a valid storage format. I'm not asking you to really implement the kind of data storage bit packing part, but you can. I hope that you can agree with me that in principle this can be done after you separate the signal into sine part and noise part and encode them separately. Okay, this really can be you are already having your own data storage format. Okay, and so you store this format, and on the player side, that's when you synthesize you play the file, right? You play P5 file. Okay, so again, so for that same original signal,
draw every outer line first, then fill in the interior.
The data and then play the sine part, synthesize sine part on the fly.
Draw every outer line first, then fill in the interior.
On the fly.
Draw every outer line
and
first.
then what's interesting might be, what if we put the two of them back together? Will they sound even closer to the original? And I think the answer is yes.
Draw every outer line first, then fill in the interior. Draw every outer line first, then fill in the interior.
The quality is not perfect. Okay, this is just my homemade encoder, MP5. But you see that this is ideal. You achieve data compression, so you can store your sound file in this representation using your own format while creating a player that can synthesize sound on the fly. And this is an example, by the way, of using 8 parameters for LP coefficients and tracking 20 traces, 20 trajectories all the time with a frame rate of 40 frames per second. Okay? This should be 40 per second. Okay? And what's even cooler is that then you might wonder, well, we already have MP3, we already have MP4. Why bother to create another format? So my answer is this format has an advantage of allowing the user to kind of change the playback speed as well as to shift the pitch very easily. So what does that mean? So remember that if you look at the sine part, okay, look at the sine part. Amplitude, since amplitude and frequency are already separately encoded. So if you want to, let's say, if you want to shift the pitch, it's really easy, right? Just when you synthesize, before you play back, you just multiply the frequency by a fixed ratio, and then you are shifting the scale up or down by a few degrees, okay? So it is totally by some certain interval. Okay? It's totally easy to do this. Whereas it might not be so straightforward to allow a real-time control pitch using MP3 format. MP3 is totally another way of encoding. So that's a kind of benefit of creating this format of our own. so as to enable easy control of the playback speed as well as pitch shifting. And to control playback speed is also really easy too. You just change the synthesis, the frame rate at the player, okay? Because in principle, these trajectories do not forcefully tell you exactly the sound should be synthesized. It allows us it gives us some freedom to determine the playback speed at the player side. Okay, so this is kind of the nice thing about our own homemade format for encoding audio. Any comment?
I have a question. Is
Yes?
this a similar type of compression that YouTube uses to double the speed of their YouTube videos,
That's
or
a
is
good
it completely
question.
different?
I'm not sure. There are other techniques, okay, I doubt they do this, yeah. Because the kind of artifact that when you double the speed, yeah. So it'll be a very nice comparison, you know. Now after this homework, you will be able to play back the signal at double speed or 2 times slower or 2 times faster. It will be really interesting for us to see, does this sound familiar? Because now we have YouTube, right? They do this. They probably use other methods. There are some other methods available out there.
Okay, thank you.
Yeah. Okay. By the way, did I forget to play this? Did I play? Oh, yeah, I did. Okay. So yeah. So this is your new format. And next, let's look at detail of implementation. Okay. All right. So about the decomposition part, this is a thing that you need to implement. Okay. In my starter code I give you this week, the phase estimation part is already there, so you don't need to worry about this. But you do need to worry about how to subtract the sum of sinusoid from the signal. And here are the details. First of all, let's say K is the track number and M is the frame number. Okay, so for each frame, assume that the length of the frame is big M. Okay, so the time index runs from 0 to n minus 1. So you will use the amplitude, and because the amplitude is encoded in dB, right? So you need to convert it back to linear scale. And you are already given the frequency in rad per sample, okay? So omega, small omega. So with these 3 arrays, this is the way you put together a frame of sum of sinusoid. Okay, is that clear? Amplitude, frequency, and phase. Okay, pretty straightforward. And then for some reason, because of the inverse and forward of inverse Fourier transform, there's a normalization factor that actually should be taken care of, and I've taken care of this for you. Okay, so you'll find in my starter code there's a step of renormalization. Okay, you need to divide this sum by this factor gamma. Okay? I'll not talk about details, and this is the right thing to do, I'm pretty sure. And then after this normalization, then the result, then you are ready to remove the sum of sinusoid from the original signal, from the signal, in a frame by frame manner, because later you use overlap and add to reconstruct the kind of continuously running signal. Okay, so how do we do the two of this? First of all, for each frame, this is what you do. Let's say for each frame we are using a Han window. Okay, Han window and Blackman window. We use the Han window. So basically, this is pretty easy. So you take the signal at the current frame. Okay, so shifting to the left, right? So you shift our signal. So you're taking the nth block of the original signal, and you just subtract them. And after subtraction, you multiply the result by the Han window. Is that clear? So that is pretty easy, right? It is pretty easy. And then you obtain one frame of signal where all the peaks have been removed from the spectrum, meaning that all the sinusoid have been subtracted from the signal. So that's one frame of the residual. And we denote it as the nth frame of X noise. Okay? M denotes the frame number, right? And then what comes next is pretty straightforward. We will overlap and add. Okay, we shift the frame to this where it ought to be, and then we add something all together to form a kind of in a sense of overlap add. Okay, so that's the result of X noise. Any question here? And this is what I left blank in my starter code. You'll find in my starter code, these are equations that you need to implement. Okay. So that's a overlap pad part. Overlap add part. Okay, overlap add part. And next, in the next slide, I'll talk about linear prediction. So for the linear prediction part, we are going to linearly linear predict encoding of the noise part. Okay, so once you obtain that X noise of n as a sum of overlap added sum of a residual, and then you pretty much follow homework number 3 first. Okay, so just for your sake to recap, so this is the content actually in our homework number 3. So you'll take one window. Okay, so you'll take one window here. Y is X noise. Okay, you take you use a rectangle window to acquire one block, to obtain one block, and for that block you will run LPC, which gives you up to A1 to AP, up to P coefficients. Okay. So it's really one line. Really, this is one line. So you run LPC, you figure out the format. Okay, if you run LPC, I give you up to P parameters, which are called linear predictive coefficients, LP coefficients. And then the next step, once you obtain the LP coefficient, you can filter the signal in this FIR sense. Okay, and remember that in homework number 3, I urged you to really pay attention to the plus or minus sign, because sometimes on my slide, the definition might be different from that of the MATLAB. Okay, so please take care of the plus or minus sign. But if you do that correctly, you subtract your prediction from the original signal, which is our X noise, and the remaining is called the excitation source or the error signal. But this time we are going to do a follow, after you obtain the excitation signal, I want you to calculate this mean square, okay, root mean square. I call it sigma. So this is just sum of square, the mean, and taking the root, the square root. Okay, the root mean square of your excitation, because we argue that excitation should pretty much sound like white noise, because LP whitens any signal that any of the input. Okay, any question right now, right here? Is that clear? Because we can expect EN to be pretty white. That's why we only need one parameter. That's what I meant. We need only one parameter to describe, to kind of orally describe what is white noise, because all white noise is going to sound the same, right? All white noise of the same loudness is going to sound the same, right? So we only need one parameter. So that's the one parameter. So now we have P parameter of the LP coefficient plus 1 of this sigma. And then on at the player side, first, so now we come to this all pole filtering part. At the player side, I suggest that you just create an instance of the white noise, call it E prime n, because each time you need to run the pretty much random number generator, right? So if you specify the variance, then it gives you one instance of the white noise, and then use that. At the player side, use that with your filter, but now you do IIR filter, which is what I mean by all pole. Okay, all pole is what IIR filter. So so after you create this instance of white noise, you then you perform time varying all pole filtering by time varying, meaning that each frame is different, and frame wise processing. So you will. Actually, I don't think you absolutely need time, but anyway, overlap add, and then then you will perform time varying filtering by 1 over AZ. This is kind of the standard DSP notation. 1 over AZ, meaning that AZ occurs at the denominator part, so it is an IR filter. Okay, there's a command function for you to use in MATLAB. Okay, they're using the filter command. Okay, for IR or FIR, right? Any question right here? Any question right here? So this really occurs at the player side. Okay, that's the player, and this is the encoder. Okay, to give you the kind of the data that you need for storage. Is that right? Is everything good so far?
So far, so good.
Okay, so here's, yes. Okay, can I continue?
Yeah, I said everything's good.
Okay, thank you, yeah. All right, so now this is my suggestion for the kind of breaking the workload. So I suggest that you break into two teams, at least for the first week, okay? So one team should focus on the decomposition, tearing one signal apart into the sine and the noise. And the other team can focus on linear predictive encoding of the noise part, okay? And to enable that, I actually have provided several, only one actually. I have provided that example, draw every outer line first and then fill in the interior. So I provided my example of that. Example of the X noise, it's kind of intermediate. Yeah, this is the intermediate step, right? You need to have that to work on the linear prediction part, right? So I've provided this intermediate signal right here. So that the first team can expect, after your implementation is successful, the residuals should sound close to my result, I argue, at least for the same input. It will not be identical, but it should be similar, okay? Also, in the meanwhile, the second team can just use this X noise right away. Start with that, and you can just concentrate on encoding the noise by linear prediction. Is that clear? So breaking into two groups, that's my suggestion. So if you are super, say, if it turns out to be too easy, of course you can work on both. But I hope that maybe even today you can try to have a discussion. Over each group, I encourage you to have a discussion who will work on what. Okay, so that so you can just break a word into two, right? And so with that, next Tuesday, I'm hoping that you will be able to come back and exchange ideas and share with each other team of your code. Okay, so that's so idea is that in this homework, I encourage sharing your code. Okay, this is already the kind of final one of a series of 3 homeworks. And by now, just as well as I'm sharing my code to you, okay, I expect you to share your code with others. So there's no, yeah, I hope this is comfortable for everybody. So that's for the first week. The second week, of course, you will integrate your codes from both teams. And there are a lot of things you can fine tune, okay? So fine tuning for example, the frame rate, the LP order, the number of tracks, as well as maybe kind of how exactly you want to handle birth and death. Is there the kind of maximum jump that is allowed? Everything you can think of that you want to fine tune, that can be done in the second week. I also want to encourage you to try examples other than solo voice. One thing I haven't mentioned for this MP5 format is that let's say compared to vocoder, okay? This format actually allows you to have multiple F0, okay? You can try to feed it with a piece of polyphonic music even, right? Let's say SATB 4-part singing, okay, a cappella. So you can try that. Or you can try instrumental sounds, piano, guitar, violin, flute, any instrument you can think of, okay? And try to see if the S plus N decomposition still work. One natural question is if you have 2 or more voices or more instruments, maybe all you need is more number of tracks, because each instrument is going to create a series of harmonics, and another person or another instrument another series of harmonics, and they might sometimes run into each other. So there's itself a rich topic, okay, for you to explore. So you can try to encourage you in the second week to try, after you nail the kind of the basic part, try different examples other than just solo voice. And of course, in the second week, Next, you also, at the same time, you can play with time expansion or pitch shifting. They create kind of factorily sounding, no artifact, does this sound natural after shifting the pitch or after changing the playback speed? Does it sound better or worse than YouTube, for example? And to enable your kind of extensive testing, I will, in the second week, I will provide you with what is called the SQAM material, the standard quality assessment materials. Now, we'll touch that next week. Okay, it's like a set of kind of classical sound examples that people in the old time, in the 90s, they used this set of materials for developing MP3. Okay, so I'll have a copy of that. And I'll provide you with that next week. And also, let me please bear with me. I will announce the report requirement next Thursday. Okay, because yeah, this week really is for you to work without worrying about the report. Any comment here? Any question here?
I guess I have a question about
yes,
collaboration. If we're working in another language, I assume that means we need to switch to MATLAB, or are we on our own, or what do we do about that?
Right. What do you think? Do you think that the complexity you can handle by yourself? No.
I think I could do the whole thing by myself, yes.
Sure, okay, but still participate in the discussion because the principle of mathematics is the same. Right?
Yeah, I can definitely participate.
But you might want to switch to kind of leave your nonlinear oscillator alone for this week, because other people are not going to work on that synthesizer.
Yeah, that makes sense. I'll leave that behind and then work on the more traditional algorithm.
Thank you. Anybody else? Okay, so now the final page, starter package. In today's starter package, I provide you with a few files. The main file right here is named as ASS Homework 7 Starter. Okay, that's the main file. And I intentionally left blank a few crucial parts that you will need to fill in the detail. And then I also upgraded my subroutines, the finding peak part and the added synth part. I named them my find peak 2020, my added synth 2020. Okay, so the details of what's new is right is here. So in the finding peak part, the code now incorporates large jump prohibition. So I intended, now in the code you find, I intended all the peaks to have to enforce social distancing of 50 hertz. They cannot, social distancing. I found it amusing to call it social distancing for the peaks. And then also the phase of the peaks is also returned, and you can use that for S plus N decomposition. You'll need that. Okay, so that's a new update. What's new for the peak finding part? And the new thing for the added synth part. First of all, I'd like to thank one of you. I forgot which one who pointed out a typo of my old code on Tuesday. Who is that? 自己承认. I really want to thank you. 我把一个地方1打成3还是3打成1 I check. You are right. 谁自己承认好吗？是谁？ I want to know. I really want to know. Group 4 的 presenter 是孟汉吗？是吧？是你吗？ Okay, good. I really thank Group 4 for the contribution. Great. 保证不加分。我们不要为了分数。Okay. So yeah, so that's one tiny thing, and also I want to say that I like to thank Mo Ziwei. Okay, so I'm incorporating his idea of peak continuation without explicitly storing the trajectories. I found it to be kind of inspiring. Okay, so we handle birth and death internally at the player side. Okay, so I found that to be a great idea. So the only drawback I can think of is that perhaps by doing so, there is still some drawback. There's something to gain, something to lose. So let me, I'm not going to say what exactly is the drawback in my mind. But anyway, in this new added synth part, I'm incorporating peak continuation without explicitly storing the trajectories, which really simplifies the data format. There's the main file, and also in the folder on e-learning, you'll find a zip file, which is called ALPC 20 signs frame rate 40. Which means that we keep track of 8 coefficients, 20 signs at the rate of 40 per second. And you will find the intermediate step. That's important for Team 1 and Team 2. The N part, the noise part before and after LP encoding. Okay, and I've also uploaded this PPT, so that's all the materials I have with you. And so yeah, so that's all. That's all.
老师，那个分组是要怎么分？会有提供那个分组的配对吗？
没有啊，就是原来的组，但是我是说那个你们组内自己 within your group you discuss who work on team 1, who is team 2.
了解了解。
Yeah, this is up to your preference. Yeah, if you are more interested in the LP part, work on the LP part. If you're more interested in the decomposition part, work on the decomposition part. Is that clear? 大军这样可以吗？
Okay, it's clear.
好，好，好。那我要怎么样？好 ，Let me start recording now.